Look at this 3D grid. As the linear transformation takes effect, the vectors stretch and the entire space instantly skews and shifts. Mathematically, this action is executed by a matrix A, an m by n array that takes an input vector x from n-dimensional space and maps it to an output vector b in m-dimensional space. Watching this geometric warping is visually satisfying, but the raw numerical array of the matrix itself is opaque. The numbers alone hide how the space is actually bending. To define this transformation with precision, we have to extract its structural parameters. We need to systematically find the exact basis vectors that define the underlying subspaces of the map. We cannot extract those bases by looking at the unreduced data. To expose the true geometric capability of the space, we must decode the matrix algebraically. This diagram illustrates our primary diagnostic tool, the Row Reduced Echelon Form, often called RREF, or the trepinormal form. Here, we set up an augmented matrix and apply a series of standard row operations. Gaussian elimination performs a systematic structural dissection of the linear map. With one complete pass through the algorithm, this final reduced form decodes three distinct properties of the matrix: its invertibility, its image, or build, and its kernel. The row-reduced echelon form bridges abstract linear algebra theorems with concrete operational calculations. To determine if our matrix A has an inverse, we augment it with the identity matrix IN and begin the row reduction protocol. On the left side of this split screen, the algebraic operations manipulate the rows. On the right, we track the geometric reversibility of the transformation. If the left side reduces perfectly to the identity matrix, the system is reversible, and the right side becomes the exact inverse matrix, A inverse. If the reduction encounters a non-pivot column before reaching column n, the algorithm halts. A single non-pivot column proves the matrix is singular. It maps multiple inputs to the exact same output, rendering the transformation mathematically irreversible. Next, we evaluate the kernel, or build. This is the set of all input vectors x, where the transformation collapses them to 0, solving the equation ax equals 0. Returning to our diagram, we focus entirely on the non-pivot columns isolated within the reduced matrix. In this algebraic system, these specific non-pivot columns correspond to our free variables. Parameterizing these free variables, setting one to a distinct value and the rest to 0, allows us to extract a set of linearly independent basis vectors. These specific basis vectors span the exact null space of the transformation. The kernel is the exact geometric subspace of inputs that collapse into the origin, quantified by the parameterization of the non-pivot columns. We must also map the reachable output space, known as the image or build. This is defined as the span of the column vectors of A. This time, the diagram highlights the pivot columns in our reduced matrix, drawing lines backward to the corresponding columns in the original unreduced matrix A. The pivot columns in the reduced matrix indicate the locations of the basis vectors, rather than the vectors themselves. We extract the actual basis vectors from the original matrix A using those specific pivot locations. The pivot columns act as indices, pointing us to the linearly independent columns of A that construct the entire reachable output space. The relationship between the input variables and these subspaces is governed by the Rank-Nullity Theorem, or dimensions formula. The equation states that n, the total number of columns in our matrix, must equal the dimension of the image plus the dimension of the kernel. We map the dimension of the image to the count of pivot columns, defining our rank. We map the dimension of the kernel to the count of non-pivot columns, defining our nullity. Every input dimension faces a binary geometric fate. It either survives to expand the output space, or it collapses entirely into the null space. We can apply the extracted image and kernel to define the geometric structure of an inhomogeneous system, where AX equals a non-zero vector B. A solution for X exists if the vector B is an element of the image of A. When this condition is met, the total solution set, these LA of B, equals a specific solution vector, x0, plus the kernel of A. Here, in a 3D coordinate system, a plane representing the kernel passes through the origin. We plot a specific solution vector, x0. We translate the entire kernel space along x0, shifting it to form a new affine subspace. The solution space to an inhomogeneous system is a precise affine replica of the kernel, shifted rigidly through space. In the case of an invertible matrix with full rank, the row reduced echelon form evaluates exactly to the identity matrix. Because it is the identity matrix, there are 0 non-pivot columns, leaving the kernel strictly as the 0 vector. A kernel of 0 causes the affine solution space to collapse. The entire shifted plane shrinks down to a single unique solution point. Gaussian elimination exposes the geometric anatomy of the linear transformation.